tracking two hands interactions, and it is sponsored by the Facebook Reality Lab. And this is Yihui and Amrui, and our advisor are Shou-Yi and Katerina. And this presentation will consist of two parts. Firstly, we will go through a brief summary of our project, and then we will report our progress in the past, present, and future 3 parts. So what is the motivation of our project? On the one hand, for the Facebook Reality Lab, as you can see from the video. This is a video clip from what they present in the F8 2019, 3 days ago, and on the Facebook Developers Conference. And they can now generate really realistic facial reconstructions and for the virtual communication. But you can see the woman used her hand unconsciously to express herself. That is because the hands are surprisingly important to convey information during the communication. So it will be very beneficial to reconstruct the hands along with the head, and it will be very natural to see a floating, talking head along with two moving hands. So, and on the other hand, for the research part, the hand pose estimation and tracking is more technically challenging than the body and face, because it is more there is more occlusion and deformation exists. So this is our motivation. The problem is defined as the following. The task is very simple. It is the head-to-hand pose estimation, and possibly we may have mesh tracking, and also the data received from the Facebook Reality Lab is just sequences of images of hands captured from multiple cameras in multiple views. So the solution we propose, firstly, we think whatever methods we want to use, we need feature extraction from 2D images, and then we can aggregate these features into a 3D prediction. So how can we combine the 2D features to 3D? We can either use the prior to learn from the neural network to directly predict the 3D positions, or we can aggregate the multiple view from the 2D features into 3D. And if there's time permits, we may also try the structural learning and time persistency, if possible. So, you will talk about what we did in the past.
We first established our baseline on basics to the key point detectors. The key point detector we use here is hourglass network. It's a stack of several hourglass network. Basically, this whole network have a downsample ratio of 4. So if the image size is 224, it's divided by 4 in the output map. Since our data is multi-view sequential data, during testing, we first obtain the key points in each view, and we use triangulation and ransack in the second paper to obtain a 3D key point structure. Specifically during the ransack, on each step, you randomly select 2 views to generate a 3D joint by triangulation. And then this 3D joint is reprojected to other views to rule out outliers. Here are some results. we showed here some failure kits. As you can see in the frontal view, even though there are some drugs that are visible, they are still not detected by this method. We think the main issue here is RunSec relies on most some view to work. If there's only like one or two views that works, this method will fail. Here are some quantitative results. So it's quite obvious that on thin and single hand, the method performs best. And for two hands, there are occlusion. And for novel objects, it's become harder since the distribution is different. Next, we tried some more recent method, keep on lifting. This is the ICCV 2017 paper we implemented. It's really keep on lifting from single image. The network receives an RGB image and first gets the segmentation, and then from the segmentation and the detected key points, there's a lifting line to lift the 2D key point to 3D key point. Specifically, the 2D to 3D lifting key point have two streams. The first stream predicts a predict key point of canonical view. The hand is canonical so that the length from wrist joint to the middle MCP joint is 1, and this bone is facing towards the camera. And the second stream is responsible for predicting the viewpoint RMT. These two streams during training are supervised independently, and the final results are obtained by multiplying them together. These are some our re-implemented results on the OSIS data set. And we get average error per endpoint of 25 millimeter. It's quite high. And these are some successful cases and failure cases. Since this paper only tests their method on the data set which do not have multi-view, and in our data set we want to use the multi-view advantage to see if this method can be better than the first method we tried. We can simply average the prediction from each view together, and this is a result on our data set. And just look at the last row. There are 3 subjects, so we come to a different result. For the orange numbers are median of all the 3D joints predicted by this network, and the black numbers are the mean. So EP mean global is a 3D joint predicted by all views averaged together. Compared with the first method, which only have average error of 4 millimeter, and this is quite high. We conclude that the prediction from lifting network is quite noisy, since the network only take advantage of a single view instead of multi-view during testing. The multi-view is simply average, but they don't use RLT of the non-camera rotation. So really I'll talk about our current work about making this better. We further test a more simple version of the SSA 17 paper. Instead of using an hourglass to detect the key point and then lifting the key point to 3D, we can simply use a ResNet 50 to predict the rotation and the canonical pose from the image. And it turns out it also works very well. The endpoint error is only slightly worse than the SSA 17 paper.
So since last presentation, despite the goals he talked about just now, we also want to find new feature fusion methods that can combine the features during the training in the end-to-end fashion, just like what he said. They can take a look at the feature from the other views and improve the features for themselves. And we also want the network to be able to update the feature representation during the training. And if you see a new view, you can expect it can be improved. So we find this new paper. It is called Learning Spatial Concepts with Geometry Aware Recurrent Neural Network. And it is presented by our supervisor, Katerina. And it is a paper from CVPR 2019. And the GRNN, and it can also be called GRNN. And the GRNN learns to lift and integrate to the image feature to 3D from multiple views. And this architecture is actually trained given a straw sequence of images from multiple view, and the sequence consists of static scenario, and the camera just goes through the static scenario. But in our setting, if you see the video at each time step, it is exactly equivalent to their setup, because we also have multiple views, and we can send the multiple views into the model one by one. And this is the overview of the architecture, and it is quite complex. So I will just talk about the module level idea here. So at each time step, there is an image. At each time step, the RGB image will be the input, and then it will be the input for a 2D encoder-decoder escape connection network, that is a UNet, and get the 2D image feature. And then the 2D image feature will be projected to a 3D image, to a 3D feature, which is actually a 4D tensor. So this VT is the 4D tensor. Then the 4D tensor will be the input of a 3D UNet to get a BT bar, which is the latent feature for this exact viewpoint. So this BT bar is the feature from this viewpoint. And then using the eagle motion prediction module, it will be oriented to VT bar prime. That is to send the coordinate system to the coordinate system with the reference view, and it cancels the relative camera motion between the current view and the reference view. So all the VT primes are in the same coordinate system. And then it will send to the GRU to make the GRU memory state to update to a new memory state NT. And this is the updated latent representation after seeing this new view. So it can aggregate multiple views information and keep updating the latency representation through new point views. So this is the refined representation, and it can be either projected to a specific view if you keep a query view, and then you can decode this into a corresponding RGB image to finish the view prediction task. And also you can feed this into a 3D mask RCN network to get either 3D bounding box or 3D mask. So this is the whole pipeline, and we are currently re-implementing this method, and we haven't finished yet. And its implementation does not rely on the internal data, so we can work on it during the summer. And we hope we can discuss more details about this at the beginning of that next semester. And successfully adapt this method into our data set.
So in the future, we plan to first finish the GRN on our data set. Then we will try to compare GRN's performance with previous two methods. And finally, since we have many views, we want to try some attention methods to focus on views that predict a better viewpoint. That's it.
Any questions, like from the faculty and staff and PhD students first?
How is this unprojection there?
It's like in the 3D grid IJK, then you will look at the image at the position. It's like I divided by k is equal to x divided by f. So you can have the f times the I divided by k is the coordinate for x. So for each grid in the 3D model, you can have a corresponding pixel in the image, and you just copy all the image along the voxel, along the ray. So, and it is the first part, and the second part is it will go through another unit to get a mask. It's kind of binary voxel to represent whether there is some information occupied in this voxel, and will multiply together and go through this 3D unit to get VTR. So it's a ratio.
Yeah. Also, do you have an underlying assumption on the data that you are measuring? So, under what condition your system is working? You know, like big perspective, projection, full perspective. So, based on the camera model, are you modeling that directly, or you hope that the system will learn? So, for example, when you collect the data of the hand videos, do you have an assumption of that type of camera that you are using? Big perspective, like a still orthographic, or big perspective? Yeah, so basically you presented that two-stream network. That's basically a factorization method. You have the video, you want to factorize it to shape and motion.
So carrot, yeah, no, in our data set.
So you hope to learn that somehow.
We know carrot.
We know the extrinsic, intrinsic for the cameras, and if you use this method, actually it does not require you provide the RT but we have the ground truth.
Also, you have the ground. And do you want to compare it to other structure from motion properties? So you can measure, I mean, that would be a nice baseline, right? Because a big part of this problem is kind of solved in autonomic manner. So if you can track two key points, you can solve this structure from motion under certain conditions.
So are we going to make this run of yours or close to this is a this is a big network, so and it has, that's what I'm saying, like so much is all faster to run, and probably my time for part of this like this huge network, and this is probably slower than us to run
Well, how hard is the challenges there dealing with exclusions from the staff and from the 3D research, which always makes it very special that you can do and operate.
If the
Like one of the biggest challenges is
Right.
you're dealing with occlusions. Occlusions are one of the biggest challenges in computer graphics when you try to synthesize images. Right? It's these sharp discontinuities that you need to contend with when you're trying to render out images. And in some ways it's a much simpler version, but occlusions is still present here. I'm wondering if there's anything special that you need to take into consideration when you're dealing with that here.
Right, but from our previous experience on the 2D to 3D, the error mainly comes from the inaccurate coupon estimation. So, bulk copos, the rotation and translation estimated pretty well. So I guess it might be the same case in this method.
Okay, just want to make one comment. So, Laszlo was asking you about what's the camera model assumption. So if it was like orthographic, weak orthographic, half-line perspective. This is a comment that a lot of people in computer vision, senior people have, is that the new generation coming in, they do a lot of statistical learning, but like the basic computer vision knowledge in certain areas is like really weak. So when Laszlo asks a question like that, like, what is the camera model assumption? Like, you should be able to say perspective. Instead of R, saying, are you talking about R, are you talking about T, are you talking about K? It's a special type of K, right? Okay, so this is kind of for the whole class. Like, let's try to have a balanced education. Okay? All right. Thank you.